All right, this lesson is on independent and dependent events, and in it we will be, our objectives are to determine whether events are independent or dependent and to find the probability of independent and dependent events. So we're going to talk about independent, dependent events, and conditional probability. So, events are independent if the occurrence of one event does not affect the probability of the other. So if one does not affect the other, they are independent. If a coin is tossed twice, its landing heads up on the first toss and landing heads up on the second toss are independent events. So the first toss you may get heads or tails, and the second toss, again, you could get heads or tails. But the first one does not affect the second one. The outcome of one toss does not affect the probability of the other. So, to find the probability of tossing heads twice, you're going to multiply the individual probabilities. The probability of getting heads the first time is 1/2. The probability of getting heads the second time is also 1/2. We multiply them, and the probability of getting heads both times is 1/4. So, if A and B are independent events, then the probability of A and B both occurring is the probability of A times the probability of B. So, if the events are independent, multiply the probabilities. Here's an example. Let's say we have a 6-sided cube, and it's labeled with the numbers 1, 2, 2, 3, 3, and 3. 4 sides are colored red, 1 side is white, and 1 side is yellow. Let's see if we can find the probability of tossing a 2 and then tossing it again and getting a 2 again. Tossing a 2 once does not affect the probability of tossing a 2 again. So the events are independent. That means that to find the probability of a 2 and then a 2, I can multiply the probability of finding a 2 the first time times the probability of a 2 again. And we know that 2 of the 6 sides are labeled 2. And so that means we have 2 out of 6, or 1/3 for the first probability of 2, and then another 1/3. 1/3 times 1/3 gives us 1/9. So that was 2 out of 6 reduced to 1/3 there. All right, so now let's say we have a 6-sided cube and it's labeled with the numbers 1, 2, 2, 3, 3, and 3. 4 sides are colored red, 1 side is white, and 1 side is yellow. Let's see if we can find the probability of tossing a red, then a white, and then a yellow. The result of any toss does not affect the probability of any other outcome. Each toss is separate. Each one is independent. So, if I want to find the probability of red, then white, then yellow, I can just multiply probability of red times probability of white times probability of yellow. 4 of the 6 are red, 1 is white, and 1 is yellow. So I'm going to have 4 out of 6 times 1 out of 6 times 1 out of 6. 4 out of 6 for red, 1 out of 6 for white, and then 1 out of 6 again for yellow. Multiplying straight across the top and straight across the bottom reduces to 1 out of 54 for my probability. Events are dependent if the occurrence of one event affects the probability of another. For example, suppose that there are 2 lemons and 1 lime in a bag. So we have 3 pieces of fruit in the bag. If you pull out 2 pieces of fruit, the probabilities change depending on the outcome of the first. So if you pull out, depending on what you pull out first, it's going to affect what you pull out second. The tree diagram shows the probability for choosing 2 pieces of fruit from a bag containing 2 lemons and 1 lime. So the first draw, you either get a lemon or a lime. Then from there, the second draw, again, you either get a lemon or a lime if you had drawn a lemon first, or if you drew a lime first, on the second chance you can draw either a lemon or a lime. And we've put the probability of getting those things next to each one. The probability of a specific event can be found by multiplying the probabilities on the branches that make up that event. For example, the probability of drawing 2 lemons is 2/3 times 1/2, which was 1/3. So the probability of drawing 2 lemons, looking at the diagram, that would be this branch here. If I want to find the probability of drawing 2 lemons in a row, I have to multiply. The first time I have 2/3 because there's 2 lemons in the bag out of 3. And the second time I draw, I only have 1 lemon left in the bag out of 2 objects. Multiplying those together, it gives me the 1/3 for the answer. Oh, I put the picture right here. Could have looked right here to see it. To find the probability of a dependent events, you can use conditional probability. The probability of B given A, probability of event B given that event A has occurred, and that's what this symbol here means. If A and B are dependent events, then the probability of A and B equals the probability of A times the probability of B given that A has happened, where probability of B given A is the probability of B given that A has occurred. So whenever we see this, I'm reading it as B under the condition of A, or the probability of B given A has happened. So that's what this symbol, that's what this means, that little slash. Okay, so this is like, for instance, saying, what is the probability of picking a second lemon, assuming that you first picked a line? So that's, in order to say that in this terminology, you would say probability of lemon given, this line given, that you've already chosen a line. So, okay, let's look at an example of this. 2 number cubes are rolled, one red and the other blue. Explain why the events are dependent, then find the indicated probability. Okay, so we have 2 cubes that are being rolled. So here's a diagram having 2 cubes being rolled, a red one and a blue one, and you can see that each pair is a possible outcome. The red cube shows a 6, so we want to find the probability. The red cube shows a 6, and the sum is greater than 9. So let's see, what is the probability that that the red cube is a 6? Well, the probability that the red is a 6 is down here. We can see that there are 6 options, 6 outcomes that have a red 6 in them. Okay, each one of these, 1 and a 6, or 6 and a 2, a 6 and a 3, and so the probability of a red 6 reduces to 1 out of 6. The probability that the sum is greater than 9, assuming, given that we already have a red 6, well, how many of these that are circled, assuming that we have, talking about this, how many of these have a sum that is greater than 9? 3 of these have a sum greater than 9. That's these 3 here, all right? 6 and 4 would be 10, 11, 12. Those ones add to more than 9, so we have 3 out of the 6, which reduces to 1/2. The events, the red cube shows a 6, and the sum is greater than 9 are dependent because the sum is greater than 9 is different. The probability that the sum is greater than 9 is different when it's known that the red 6 has occurred. So, because if we weren't talking about just this space, there's other numbers up here, aren't there, that are also the sum is greater than 9. So the fact that we had to pick only ones that had red 6s affected our choice. So because they depend, that's why, so they depended on each other. They are dependent events. Okay, let's see if we can find the probability then. We're going to use the formula, the probability of A and B, probability of A times the probability of B given A. So plugging in our things, the probability of red 6 and sum greater than 9 is the probability of a red 6 times the probability of sum greater than 9 given red 6. And those are the 2 probabilities we just found on the other slide. 1/6 for the first one and 1/2. When we multiply them together, the probability of A and B is 1/12. Two number cubes are ruled, one red and one blue. Explain why the events are dependent, then find the indicated probability. The blue cube shows an even number and the sum is 5. So the blue cube shows an even number. The events are dependent because because the probability is different when the blue cube shows an even number. You can't see the word probability there, but the probability is different when the blue cube shows an even number. And so these are the ones that have a blue cube with an even number, either all 2s, all 4s, or all 6s. So out of the 36 outcomes, 18 have an even blue number. So 18 out of 36 gives us half of them have a blue even number. Out of those 18 that have a blue even number, 2 have a sum of 5. Either we got a 3 and a 2 or a 1 and a 4, and those are the only two here that within what I've circled that add to 5. So that's 2 out of the 18 that were circled. So the probability that the sum is 5, given that we're talking about a blue even number, is 2 out of 18, or 1/9. So now we can find the probability that blue is even and a sum is 5 by using the formula. Okay, so we're going to do, this is going to equal the probability the probability blue is an even number times the probability that the sum is 5 given blue is an even number, which are the two probabilities we just found. We multiply them together and we get 1/18 for our answer. Conditional probability often applies when data falls into categories. Let's look at one that has a chart. The table shows domestic migration from 1995 to 2000. A person is randomly selected. Find each probability. Okay, so let's use our chart to find the probability that first, let's see if we can find the probability that an immigrant is from the West. So looking on here, we're going to have to find the probability of immigrant. So we're going to need to add up how many immigrants we have in that column. And in this column, the immigrants adds to 11,656. So out of that total, how many of them are from the West? The probability of West given immigrant is dividing those two numbers, which gives us 0.228, about 23%. Now, what's the probability that someone selected from the South region is an immigrant with an I here? Okay, so we're talking about the South region. We're going to need to add up how many people total are South. Okay, and this row here adds to 8,285. And of those, we're going to use the number from the immigrants with an I category. And dividing those two gives us 0.609, or about 61% chance. And lastly, what is the probability that someone selected is an immigrant and from the Midwest? So what's the probability that both things happen? Well, we can know that the probability of immigrant, so we're going to have to, we already added those up. That's how we had our 11,000 number for that one. And from the Midwest, that's this number off the chart. So when we divide those two, we can get our probability for that. So now, the probability that someone is an immigrant and from the Midwest is going to be the probability of immigrant times the probability of Midwest given immigrant. Okay, so the probability of immigrant is what we got for our total immigrant column out of the total number of people. And there's 23,311 total people if we were to add both columns together. And we multiply that. In many cases involving random selection, events are independent when there is replacement and dependent when there is not replacement. So we're going to be doing some facts with a deck of cards. So remember, a standard deck of cards contains 4 suits of 13 cards each. The face cards are Jack, Queen, and King. All right, so let's say we have 2 cards drawn from a deck of 52. Determine whether the events are independent or dependent. Find the probability. What is the probability of selecting 2 hearts when the first card is replaced? Replacing the first card means that the occurrence of the first selection will not affect the probability of the second selection. So the events are independent. The probability of heart, given that you have a heart on the first draw, is just the probability of heart times the probability of heart. And there are 13 hearts. 13 of the 52 cards are hearts. So 13 out of 52 times 13 out of 52 gives us 1/16. What's the probability of selecting 2 hearts when the first card is not replaced? Not replacing the first card means that there will be fewer cards to choose from, affecting the probability of the second selection, so the events are dependent. So we're going to have the probability of getting a heart for the first card, but then when we draw the second card, we're going to do the probability of that heart, given that we're already missing the first card, which was a heart. There are 13 hearts. 12 hearts and 51 cards are available for the second selection. So the first time there were 13 hearts in there and 52 cards total, but the second time you only have 12 hearts left and 51 total cards. So multiplying straight across the bottom and top gives us 1 out of 17 for our probability. A queen is drawn, is not replaced, and then a king is drawn. Not replacing the first card means that there will be fewer cards to choose from, affecting the probability of the second selection. So the events are dependent. The probability of the queen, and then we're going to have to multiply the probability of getting a king, given that the first card was the queen. There are 4 queens, and there are 4 kings. So the second draw is going to be 4 kings, but there's only 51 cards available for the second selection. So we have 4 queens out of 52 times 4 kings out of 51. Multiplying straight across the top and the bottom gives us 4 out of 663 for our probability. So in this lesson we learned about independent events. Those are the occurrence of one event does not affect the probability of the other. Dependent events, the occurrence of one event affects the probability of the other. And conditional probability, the probability of B given that event A has occurred. Great.